Hello, everyone. This is the Academic Data Science Alliance Special Interest Group meeting. We're going to be talking with Dennis Wei from IBM about the AI Fairness 360 open source toolkit. A couple of housekeeping notes ahead of time. This event, like all Academic Data Science Alliance events, is governed by our code of conduct, and I'll drop a link to that in the chat here in a moment. I'll also drop a link to the Academic Data Science Alliance website where you can find other events related to Academic Data Science Alliance and our job board and other interest groups and things like that. So I'll drop those into the chat here in a moment. And a reminder that we're being recorded. So if you don't want to be on camera, to turn your camera off and to keep your microphone muted. I will now hand things over to Dennis, and he can introduce himself and we'll get things started. So Dennis, have at it.
Right. Thanks very much, Steve, for the introduction and for inviting me to give this talk. I'm a research staff member at IBM Research. I belong to the Trustworthy AI department, and I'll say a bit more about what it is we do in a couple of slides. So I have two topics closely intertwined today. One is fairness in machine learning in general, and the second is the actual AI Fairness 360 toolkit and the solutions that it offers for fairness. And the website for the toolkit I've already listed on the title slide here. Happy to give it out later too. Okay, so in a bit more detail, what I plan to cover today is, first I'll talk about the general topics of trust and fairness in machine learning. I'll talk about where this unfairness comes from, how can we measure it, what we can do against it, how to mitigate it. And then I'll talk about the toolkit itself, and if time permits and if you're all interested, I can show a brief demo from the website for the toolkit. Okay, so the reason that trust and fairness have become such large issues in machine learning and AI is that these systems are being used to power, increasingly critical and consequential workflows. So these are decision-making scenarios that affect human beings and affect their outcomes in important ways. So, for example, in giving out loans to people, we're enabling them to pursue various objectives in life, such as, for owning a home. In employment, these AI systems are helping to decide who gets hired and who advances in those jobs. In customer management, customers want to know that they're being treated well, being treated fairly. They want to be explained to when, certain things are done for them, particularly things that are maybe not to their liking. And in quality control, if take as an example, food quality control, the outcomes are definitely, are clearly of a societal importance, and we want our systems to be as robust as possible. So what does it take to trust a decision made by a machine or a machine learning system? Our stance, besides that system being as accurate as we can make it, is that it takes multiple dimensions, right? So the one that I'll be talking about today is it fair dimension, the fairness one. Others here are, is it easy to understand? So this gets to interpretability or explainability of the system. Did anyone tamper with it? This gets at robustness, adversarial robustness, and more general kinds of robustness. And lastly, is it accountable and transparent? Are facts about the system being recorded appropriately? Can the processes being used that were used to develop the system, can they be inspected, and so forth, right? So as I said, I belong to the Trustworthy AI department at IBM Research. The members of my department are interested in all of the questions on the previous slide, right? So fairness, explainability, robustness, transparency. We have actually developed, besides the AI fairness toolkit that I'll be talking about today, we've developed similar toolkits targeting these other dimensions of trust. The websites for those are listed here. They all have the 360 theme in their names. And so besides that, we like to work in this kind of cycle that's being depicted here. So, at our core, we are scientists, we're researchers. We like to develop new techniques to improve things along these dimensions. And then we take those techniques and try to have impact in various sectors. So, today's talk is going to be on an open source contribution in fairness, but we also have impact on IBM products. The beneficial societal deployments refers mainly to various social good projects that we've had through our social good initiative and so forth. Okay, so let me get more specifically into fairness now. So I'll start with some definitions just to kind of level set. So we'll start with justice. Say it's the moral and ethical treatment of people. There are two kinds of justice that are somewhat relevant here. So procedural justice is fairness in the rules and the processes used to determine outcomes or allocate resources. Distributive justice has more to do with the fairness of the outcomes or the resource allocations themselves. Fairness in machine learning has been mostly concerned so far with distributive justice and allocations of various benefits, but you can see that procedural justice could come into play as well, in terms of the machine learning system treating people equitably, in a consistent way. So clearly, this question of fairness has been a concern, a human concern for decades, centuries, right? There are many disciplines that have come at this from different angles, philosophy, politics, economics, and so forth. The machine learning view, is just one more angle, one more tool to examine this question. As I mentioned, it's focused a lot on distributive justice so far. There's clearly no one single silver bullet, to resolving this problem. So machine learning has become another tool, but in itself, it also leads to unfairness, as we now clearly know, as evidenced by all these headlines. All right, so at one point, we're past this point now, but at one point, we might have naively thought that since human beings are clearly biased in their decision making, they have their personal biases, cognitive biases, biases that they inherit from societies. One might have thought that if we took the human beings out of the equation and made decisions based on data and algorithms, that a lot of these bias issues would go away. Now, we clearly know that that's not the case. These machine learning algorithms, these machine learning models, they still have to learn from someplace, and that someplace, in many cases, has to be us, right? And so they embed the biases that we have into their models. And what makes it, maybe more pernicious now is that these systems are designed to be deployed at scale, right? So now the problem of bias is also scaled up. Yeah, so I mean that's clearly a reason to have this talk today, to find ways to address this problem. I'll talk about, I want to mention two different settings for fairness in machine learning. So the first one, which I'll mainly focus on today, is on the allocation setting. So as I mentioned, this has to do with allocation of various benefits, of loans, of jobs, college admissions, etc. Oftentimes these are posed as classification problems, and in particular binary classification problems, where one of the classes is where you get the benefits, the good outcome, and the other one is where you don't get the benefits. There's also fairness in terms of representation. So examples of this might be search engine results, embeddings of words that are used in natural language processing, and the connotations that those words could entail. So fairness is an important question in representation as well. These tend to have more indirect effects on outcomes than the ones under the allocation umbrella, which are kind of direct effects. Okay, so let me now get into where the sources of bias are in machine learning and ways we can measure it. Let me just check the time here. Okay, so the first thing that I'll say is that in the machine learning literature, there have been many definitions of fairness proposed. According to one source, there are more than 21 such definitions, and that source was from a few years ago. So you can imagine there are even more now. This is not just a theoretical or an academic question, because depending on the fairness definition you adopt, the way you mitigate unfairness is different, and thus the outcomes that your system produces can be quite different, right? So this is a decision that has consequences, but it is also the decision that each organization, each stakeholder needs to make, right? Depending on the application, depending on the particular values in play, one does need to decide on which fairness definition makes sense. Some people have expressed the view that all of these definitions of fairness have been proposed. We're still waiting for somehow the community to settle on one magic definition. I'm not really sure why people say that, because these questions have been debated, as I've said, for decades and for centuries. Reasonable people on different sides with different value systems can agree to disagree on what constitutes fairness, right? So I don't think we're ever going to get to a state where there is one single definition of fairness. It really has to depend, and one really has to make some value judgments about what fairness means in a particular context. So having said that, we can look at where sources of unfairness arise in machine learning. And people talk about algorithmic bias, but oftentimes the bias has to do with the underlying data on which these models are built, on which these algorithms run. So bias from data can come in a couple of different forms. One is oversampling and undersampling, right? Where we might oversample from some particular groups, while undersampling or ignoring or neglecting other groups. Labels can be biased in part because oftentimes the data that these machine learning systems are built on are historical data, and they reflect historical inequities and prejudices that people in the past may have had, and that are reflected in the decisions that were made in the past. I'm trying to remember what there was one thing I wanted to bring up here, right? So One example of selective sampling that you may be aware of is a few years ago, there was this famous study done of facial recognition systems, commercial facial recognition systems that were mostly trained on lighter skinned male individuals. So in terms of the accuracy of these systems on lighter skinned males, it was very high in the high 90%. When these researchers tested the same systems on, say, darker skinned females, the accuracy was much lower, in the 60% range. And this was largely due to undersampling in the data, oversampling and undersampling. And that can have real consequences if these facial recognition systems are used in, for surveillance or other such applications. You might ask, is the only problem, the fact that these data sets contain these so-called protected attributes like gender, like race. If we drop them, if we drop these variables, is the problem solved? And of course it isn't, because there are other variables that are highly correlated with them. So this map illustrates the point about this practice called redlining, where lending institutions used to base their decisions on zip code and on geography, which, as you know, is highly correlated with people's race, people's income status. And on the face of it, these decisions were made in a neutral way based on zip code. Whether they had discriminatory intent or not, the impact on different races, on people of different incomes, was very real and was disadvantageous towards certain races and income levels, right? So just because you're ignoring race as a variable doesn't mean you can have very, very real and very discriminatory impacts. It can be helpful to think about bias entering at different levels. This figure kind of encapsulates some things that I've been talking about. We can take the construct of creditworthiness, for example. So that's a construct, right? Someone is creditworthy or not. Of course, it's not something that we can actually measure directly, right? So we measure it indirectly through various observables that we happen to have in society, things like credit reports and credit scores. So these are things in the observed space. These observables can introduce some social bias. Some people might, these observables, these things like credit scores might be a bias towards certain groups. Certain groups of people might not have credit scores at all, right? And that can be a problem. Another level of bias comes in when we take those observables now and construct a data set. So there's a sampling process that goes on here in terms of which observables and which people we include in the data set. And this introduces population bias. This is where things like oversampling and undersampling come in. And there can be further biases introduced by how we prepare the data as well. Okay, so let me shift now to defining some terms that I've been kind of talking about informally, but we should define to get further into this. So I've mentioned this term protected attributes. So these are things like race, gender, religion. These are attributes that partition a population into groups that are usually protected by law. There is some law or regulation in the background that asks for equality or parity of some sort between these groups, right? So that's what we refer to as a protected attributes. Group fairness then is about groups corresponding to different protected attributes receiving similar treatments or similar outcomes. Individual fairness, on the other hand, is not tied to these group definitions. It simply asks for similar individuals to get similar treatments or outcomes. The challenge with individual fairness is, what do we mean by similar individuals? This depends on the context, and it can be hard to determine what we consider, what we consider to be similar individuals for a given application. A fairness metric is a measure of unwanted bias, either in the data itself or in the models. Usually this is a value that we want to reduce to 0 if it's kind of like a difference metric, or we want to get it to be close to 1 if it's a ratio type of metric. A favorable label. So as I've mentioned, a lot of the work in machine learning fairness has had to do with binary classification, where one label is favorable, it's giving people the beneficial outcome or the advantageous outcome. So that's what favorable label refers to. And the other label is the unfavorable one. So some examples of how to measure fairness. These are the most common and the most popular group fairness metrics. So the first one is statistical parity difference. So this is looking at the rate of positive decisions, I'll call it, right, for each of the groups. And so, for example, we have two groups here. One of them has a rate of 60% positive decisions. The other has a rate of 70% positive decisions. The difference then is 10%, right? So we say that the statistical parity difference is 10%. These decisions could be from the data itself, so historical decisions. So we would be talking about the statistical parity of the data itself, or they could be the model outputs, what the model is predicting or recommending. So that, in that case, it would be fairness or unfairness of the model. Statistical parity difference looks at the difference between these quantities. Disparate impact is very similar. It looks at the ratio instead. Some laws express, fairness criteria in terms of ratios. So here we take the ratio between 60 and 70% to get, 0.86 or 6/7. Equal opportunity difference is again looking at the rate of positive decisions, but we're now not looking at the whole population, but only on the subset that have positive outcomes. So these are the figures in blue here. So the blue people here are the ones who had actual positive outcomes. So let's say, again, going back to the lending scenario, say these blue outcomes are people who actually repaid their loan on time, in a satisfactory way. And the positive decisions correspond to actually giving people the loan, right? So for the top group here, of the people who would have repaid the loan, we're giving 71% of them. I might have it a little backward here. So out of the 7 people who would have repaid their loan, we're giving 5. We're actually deciding to give 5 of them. So the true positive rate, in other words, is 5 out of 7 or 71%. Whereas for the bottom group, we have also 7 people who would have repaid the loan. We are giving 6 out of the 7 the loan. So the true positive rate in this case is 6 out of 7 or 86%. And finally, the equal opportunity difference is 15%. Right, so hopefully I didn't confuse you too much from this example. You can ask me about it later, but this is just an introduction to some of the most common fairness metrics that people have worked with in a machine learning context. The last point I'll make before I pause a bit for questions is this coming back to this point of how, the choice of fairness metric that we make, how we choose to define fairness, impacts how we should measure it and how we should mitigate against unfairness. So the question posed here is, do SAT scores, so for college admissions in the US, do SAT scores correctly compare the abilities of college applicants? So if your views tend towards the yes column, meaning that the SAT score, if I look at the outcomes of people, graduation outcomes or job outcomes of people with high SAT scores, maybe yes, they do correlate well to future success. And so yes, they should be used to correctly compare the abilities of applicants. In that case, you would opt for metrics such as the ones listed here. I won't get into exactly what these are, right? But these would be appropriate metrics for that case. If, on the other hand, you tend towards the no column, if you think more that the SAT score may contain structural biases against certain groups who, because they don't have English-speaking parents or they are of lower income, they don't have access to as much SAT preparation. If you think that's more the case, then you would opt for different metrics. So in this case, the disparate impact and the statistical parity difference that I did talk about on the previous slide. So, how you define fairness, how you think about it does have consequences in terms of how you measure it and what you propose to do about it. Okay, so I've been speaking for a while. I think I'll pause here for any questions that people may have.
Dennis, do you want people to put them in the chat or just to unmute?
I think just unmuting is fine. That's okay. It's easier for me.
Great.
Although I'll take a look. I'll keep an eye on the chat too.
Hi, thanks for explaining the metrics. So in the one that we called equal opportunity metric, does that mean that there is essentially a calculation of equal opportunity? In the particular case that you described, it was how many people are going to actually pay back the loans. Is that itself a difficult thing in most cases?
Is what itself a difficult thing? What exactly?
Well, I mean, if that's not something that's observed but calculated and can be calculated in different ways, that would mean that this metric would give different results depending on the method of calculation.
Yeah. So
yeah, so I'm wondering how useful this is, or in the sense that there can be various different predictions of this metric.
Yes.
I guess, I mean, you're measuring ML bias or something like that, but this metric itself could be biased basically depending on what the prediction is.
I think you get at a good point, and I think the point is what we choose to observe or what we can observe in the data, right? So in the example that I gave of lending, ideally we would have actual repayment outcomes. We would have we would observe people for a period of time and see how they actually performed with their loans, right? That would be much better than not having that data and then having to infer that somehow, which, as you're saying, that process itself could be flawed, right? So I think it's more a question of thinking carefully about, what data do we have, what data should we have, and what are we calling a true positive here, right? Yeah, so these are important questions, and I think they even kind of predate the fairness question, right? Like, if we don't have, if we aren't training our machine learning models on the right data, or to go after the right question, right? That's a problem in itself.
Thanks.
All right, so let me go on for now. So next, I'll talk briefly about some general bias mitigation strategies. Now that we know that we often encounter this, what can we do about it? So the overall message here is that bias mitigation can take place at multiple points in the machine learning pipeline. And I'll speak more about the AI Fairness 360 Toolkit, but it enables mitigation at these multiple points in the pipeline. So in this diagram, we'll start on the left-hand side with raw data that we subject to some fairness tests. So we call these data set metrics because they measure fairness on the data itself. If we find that the data has, problematic bias, then we might pass it to what is called a pre-processing algorithm. So this tries to mitigate unfairness at the training data stage, right? Or at the data stage, but before we've applied any machine learning algorithms. So after that, either a pre-processing algorithm or standard pre-processing, we have training and testing data that's we can apply a machine learning algorithm to as usual. In this training process, we can also choose to apply what is called an in-processing algorithm. So this is one that, in addition to building a usual, supervised machine learning model, it also tries to satisfy one or more fairness criteria, right? So it's trying to achieve both objectives at once, or at least give a good trade-off between them. Right. So after that happens, we'll have a classifier, whether it's a standard one without awareness of fairness, or one that has been, in process to be more fair. This classifier will then be evaluated on the testing data, again, tested for both accuracy and fairness. So here we would come out with some classifier metrics, because these now characterize the fairness of the classifier. If that is unsatisfactory, we might go back to reprocess the data or retrain, or we might apply what's called a post-processing algorithm. So this is something that mitigates unfairness at the output of the classifier by modifying its outputs in some way. And finally, when we reach a point of satisfaction, then we can actually deploy the model and continue monitoring through this cycle. So that's the kind of the pipeline view. Here I'm just emphasizing the things that I've mentioned already, which is that there are three main places to intervene in the pipeline to mitigate bias, pre, in, and post processing, on the training data, during the model training itself, or afterward to modify the outputs. And these apply in different scenarios, right? So sometimes we do have access to and can modify the training data. And in that case, we can use pre-processing. If we can modify the learning algorithm, if we can replace it with a non-standard one that does take fairness into account, then we can consider in-processing. However, and this is actually pretty common, in this last scenario, if we already have a learned model and we can't do anything, we can't modify it, we have to treat it as is, then post-processing may be the only option. But there are still things we can do there. This slide is just further emphasizing that bias mitigation can happen early in the pipeline. I'm not going to get more into this. These are specific methods within the toolkit that we have for pre-processing. When we start, when we mitigate bias, an important question comes up of this trade-off between reducing bias on the one hand and maintaining the task accuracy or utility, the thing that the machine learning model was primarily trained to do, right? So this again comes down to a choice for the stakeholder, for the user of the model, right? One has to determine the threshold, how much accuracy is one willing to give up if it can increase fairness substantially, for example. And that again is an individual determination that has to be made. This first point is also about, this is maybe less, this is somewhat independent of fairness. This is talking about, between the two types of errors, so false positives or false negatives. Again, depending on the application, one of those may be more important than the other. And so, one should adjust the decision boundary accordingly, to favor one or the other. Okay, let me check the time. So yeah, it's, let me give you now an overview of the toolkit. I will then pause for more questions, and then if we have a bit of time remaining, I'll see whether I can show you at least a little bit of the demo of the AI fairness toolkit on our website. Okay, so the toolkit is called the AI Fairness 360 toolkit. It's open source. We at IBM Research introduced it a few years ago. I believe it was 2018. Since then, it has been donated to the Linux Data and AI Foundation. And we really do want it to become open source, where, many different people, use it, contribute to it, build a community around it, and so forth. Right? So it's, while we are the originators, we don't regard ourselves as the owners in that sense. Right? So what does it contain? We can start with the fairness metrics. So I had a previous slide mentioning that there were 21 definitions of fairness. So according to this, there are, the toolkit contains 70 plus fairness metrics. Now, admittedly, a lot of these are, variations on each other, but still that illustrates the diversity in terms of, how you can measure things. It includes 13 plus bias mitigation algorithms in all of the different stages, as ways of explaining fairness metric results, and more beyond just kind of the metrics and the algorithms that it contains. It also includes a fair amount of educational material. So We have general guidance on fairness, how to choose, right? How to think about these metrics, how to choose a mitigation algorithm. It has a demo and tutorials on some industry use cases to show how one might use these metrics and algorithms in practice. Yeah, and it's, one purpose of it is as a vehicle to translate new research in machine learning fairness into something that industry practitioners can use. So if you are familiar with scikit-learn, it uses the familiar fit predict interface of scikit-learn classes and objects. Enables extensions. And one final point I should make is that, and I think the next slide does it, is that while IBM Research was the originator of this toolkit, even from the start, it included leading algorithms and metrics from not just us, but from all over industry and academia. So I think, flashing this slide indicates that I think this is just showing the algorithm, the bias mitigation algorithms that were contributed. They come from all different sources and institutions. This is a more detailed listing of the algorithms. I'm not going to go into this except to point out this second column. So this illustrates that the algorithms, span the different intervention points that I mentioned. So pre-processing, in-processing, post-processing. Some of these methods, actually many of them, are restricted to tabular data. Some of the more flexible ones, however, in particular the pre-processing and post-processing ones, these can handle all modalities, since they're particularly the post-processing, since it's only working on the outputs of the predictor, which are modality agnostic. Let me go to the website briefly just to show, to illustrate more concretely the elements that I mentioned, and then then we can have some more questions. So let me switch over to here. Are you still seeing my screen?
Yes.
Okay. So this is the website for AI Fairness 360. As I mentioned, we have a demo of it that I can show, if we have some time remaining. We have various resources to, help people who are new to this area, start to educate themselves. I won't claim that this, should be your entire education. So, for example, there's a glossary of terms, especially helpful to people who are not, machine learning experts. There's guidance on, metrics, how to think about different metrics, how to choose among mitigation algorithms. These tutorials are so these are Jupyter notebooks, showing you these metrics and algorithms in action on a couple of use cases. There are links to the other toolkits on the other pillars of trust that I mentioned at the beginning of this talk. So on explainability, it's so forth. Of course, there is a link to the code itself, and we have both Python and R versions. The Python one is more comprehensive, but there is some coverage of a subset of the Python repository in R. There's documentation as well, of course, which gets more into how the toolkit is organized from a software software architecture perspective, what the APIs are. Yeah, I think that's most of what I want to say as an overview. Yeah, let me pause now for some more questions, and then we'll see how much time we have for a demo.
Bit of a quiet group today. Yeah, maybe we have about 10 minutes or a little more. Maybe Dennis, do you want to fly through a demo, and that might spark some questions or thoughts?
Sure. Okay, so this is the demo from the website. So basically, it walks you through the application of various fairness metrics and mitigation algorithms on a particular data set. So for a data set, let me just choose the first one here. This is a well-known data set that was published by ProPublica on criminal recidivism. So after I click next, the first thing it does is to check this data set for various bias metrics. So for example, if you take the protected attributes to be sex, female versus male, then it will report to you the values of various metrics. So I talked about a couple of these, like statistical parity difference, equal opportunity difference. And here what the plot is showing is it's showing you the value of the difference. And I think, right, so the threshold that it uses to declare fair, or whether there's a problem or not, is 0.1, I think. So right, so since it's in this pink zone, I'm not sure how well you can see it from my screen, right? It declares that there is bias according to this metric, and same for equal opportunity difference. A similar story holds if we look instead at where the protected attribute is race. So here the two groups are Caucasian versus not Caucasian. And again, there are disparities along these different metrics. So, since there is bias, we can then click next and apply a mitigation algorithm to try to mitigate. So I'm just going to pick the first one here. This is a pre-processing method called reweighing. So in the background, it's going to do its thing. So it's going to pre-process the data set. I'm not sure whether it retrains the model in this case, but in any case, it does its processing. We remeasure the fairness metrics, and we can compare, see how they were improved. So again, to take this statistical parity difference as the example, the original value was minus 0.36. It has now been reduced through the reweighing pre-processing to only minus 0.03. So this is within the 0.1 margin that was set. And similarly, a lot of these other related metrics have been improved, although this field index, which is not related, is unchanged since the mitigation algorithm was not designed to address this measure. And for race, again, it did a similar thing, and it was, I think, similarly successful. So yeah, this is just one example of how to measure bias and what these mitigation algorithms can do. I would say this is a good case, by exploring these various combinations, you can also find cases where things don't quite work out as well. Yeah, I think that's it.
Great, thank you. So any questions for Dennis about any of the variety of topics he's covered today? A few minutes for some conversation.
I have a question, and this might be very trivial, but I was wondering, like, if these different metrics of unfairness or fairness, these are not the properties of the data set, right? These are the properties of the model that we're using. Is that correct?
It can be either.
Okay.
It can be either. So in some cases, it can be like statistical parity difference, for example, can be measured on the data itself, or it can be measured on the outputs of the model.
Right. So here, when you're saying after the mitigation process is being done, is the mitigation process like training the model with an oversampled or undersampled data set, or is it just like altering the data set in some way?
Yeah, that's why I said I was unsure for this particular demo, whether it is just altering the data sets, overweighing or underweighing certain groups, or whether it is training a model on top of that. Yeah, I'm not sure for this, for this specific demo, but you could do it both ways. You could certainly do it both ways.
Okay, thank you.
I have a question about workflows. So if I'm going to use this, would I have to use everything in this toolkit, or is this something where if I'm, building a model, I could do some analysis using this toolkit, maybe run some reweighting or some other pre-processing, and then move over to my own algorithm that I'm training, and then come back and like test it again? Or do I have to kind of stay within this toolkit? And if I'm using some new innovative algorithm, I need to wait or contribute myself to the project to kind of get some new algorithm incorporated into this framework?
I would say largely that you can move back and forth between this toolkit and the other tools that you are using. That's kind of like a large scale answer. Of course, when it comes down to details, there may be certain situations, maybe annoyances where things don't quite work out that way. One example I can think of, off the top of my head is the in-processing algorithms, right, to mitigate bias within the training of the model. Those are necessarily limited to whatever has been implemented, right? So if you have, and that's a limitation of in-processing, right? If you have a particular model class that you would like to use, but there does not exist an in-processing algorithm that goes along with that model class to improve its fairness, then, but you like using that model class, right? Then you would have to look at perhaps a post-processing solution to be able to keep the things that you like about the model itself, and then mitigate its bias by different means.
Okay. Is that generally true of the other frameworks as well? The explainability? I know that's not really a topic today, but is that general answer? Does that extend to the other frameworks, like the explainability framework?
I think so, yes. So with explainability, like, yeah, again, this is not a topic for today, but one approach to explainability is to build an inherently or directly interpretable model from the start, in which case you can use our tools, some of the algorithms that we offer. The other approach is a post hoc one, where you come in already with a model that you like, and you want to apply various methods to try to explain its outputs, right? Mm-hmm. So that can be done as well.
Okay. All right, thank you.
So we're approaching the top of the hour. Dennis, I don't know if there are more questions, if you have a few more minutes to hang around and and chat. You know, if not, we want to respect your time. But yeah, if do you have thoughts on that, Dennis?
I can hang around for a few more minutes, but let me first just give just like a couple concluding comments. So,
Oh yeah, let's do that. Great, thank you.
Not anything heavy. So the one thing I wanted to one of the things I wanted to mention is that you know, if you're interested in using the toolkits, if you have questions, you know, in the process of using it, problems that you encounter, we encourage you to reach out to us via Slack. So we have a Slack workspace for AI Fairness 360, which you are certainly welcome to join. Another way that people contact us is through the GitHub itself. So by opening issues in the GitHub repository, you can communicate with us that way. I'll just very, very briefly mention that I think it would be a little remiss of me not to say that there's an open source part of AI Fairness 360, and there's also kind of an in-house version that we have, which we call the enhanced edition. So I'm just pointing out that there's more kind of under the surface that we're doing within IBM on this topic. And last message, I guess, is that, you know, preventing bias is hard. You know, a lot of people, you know, point out problems and wring their hands and wish that, you know, things could be better. But, you know, when you really get down into the trenches, you realize that it's not as easy as, you know, people would like, or one would ideally think. So yeah, I mean, we have some recommendations, but it's going to be a process, and yeah, we hope that you join us in the journey. I think that's all I wanted to say. So yeah, happy to stay around for a few more questions, or if not, end it here.
Great, thank you. Any last question for Dennis? Sounds like people are thinking about what you've shown us today, Dennis. There's a lot here, so they may be sending questions your way in the future. But thank you for coming today, Dennis. It's great to hear about this work, and thank you for your time.
Yeah,
much appreciated.
Thanks, Steve, and yeah, thank you all for giving your time to hear about this.
Great.